In the discussion of this series of chemical thermodynamics, today I shall try to explain the Nernst heat theorem. Nernst heat theorem is very important for the chemical reactions or physical transformations occurring at near about 0 Kelvin temperature. And this Nernst theorem is actually regarded as this precursor of this third law of thermodynamics. And in this introduction, I can say the T in 1902, W Rechard studied the change in free energy and change in enthalpy for the reactions occurring in galvanic cells, and he actually determined these two thermodynamic properties by the use of this potentiometer at very low temperatures. And he used this formula del G equal to minus NF E cell. E cell is the potential, cell potential, and it is determined by means of potentiometer very accurately. And he is determining these properties delta G and delta H at low temperature. This one use this formula, this T and del E cell by del T at a constant pressure minus E cell. These two properties of the chemical reactions in galvanic cells he was determining at this very low temperatures, and he found that with lowering of temperature, this delta G is approaching to this delta H of these cell reactions. And this what is very important for getting this postulate of this Nernst heat theorem. And W Rechard, he was awarded the Nobel Prize first time in chemistry in America. And when at limit T tends to 0 Kelvin, he found that del G equal to del H. These two properties found to be equal whenever temperature is very near to 0 Kelvin and some temperatures above this 0 Kelvin temperature. And these experimental results, we can draw very important conclusions by the use of these Gibbs-Helmholtz equations. And you know these Gibbs-Helmholtz equations. Gibbs-Helmholtz equations is delta G equal to delta H plus T into delta G by del T at a constant pressure. This is a very important equation, and this Gibbs-Helmholtz equations actually gives a very important conclusion on the basis of this experimental results. When T tends to 0 or some temperature above, this del G equal to del H. If these two are equal at this very low temperature, then this relation this equation gives T and del G by del P at a constant pressure equal to 0. And since these two are found to be equal at 0 Kelvin temperature and some temperature above, so when T is finite, means not equal to 0, this term del G by del P at a constant pressure equal to 0. So this is the conclusions. It means that with lowering of temperature, delta G remains constant and the slope and the curve becomes horizontal and the slope becomes 0. So this one is the conclusions. First conclusion, limit T tends to 0, del G equal to del H, and second conclusion, limit T tends to 0, del G by del P at a constant pressure is equal to 0. In the year of now I shall discuss the Nernst postulate. Nernst postulate in the year of 1906, on the basis of these conclusions obtained here, W Nernst, Walter Nernst proposed that since limit T tends to 0, del G equal to del H. So as for the condensed phases, processes occurring at this very low temperature, means condensed phases, and this one also be valid T tends to 0 Kelvin, del H by del T at a constant pressure equal to 0. These two are called the Nernst heat theorem. These two are called the Nernst heat theorem, and this Nernst heat theorem is very important, and this Nernst heat theorem is very important for the thermodynamical study of these processes occurring at very low temperatures. And actually these two equations are called the precursor of this third law of thermodynamics. Actually, I purposefully writing this T tends to 0 Kelvin, T not equal to 0, as 0 Kelvin is not unattainable. So we continue to write T tends to 0 Kelvin, and you see these two relations are valid for the condensed phase. Condensed phase means substances occurring in these processes are either solid or liquid. All these substances are in solid phase except this helium. Helium remains in liquid phase even at very near to 0 Kelvin temperature. So these two relations, very simple looking but having the far reaching implications. they are looking like very innocent, but they are having these far-reaching consequences. And these two relations, Nernst's heat theorem, if we plot in a graph, then it becomes, suppose this is a T and here del H or del G. These two are plotted against T, and this experimental cost is like that. If this is del G and this one equal to del H, means whatever with the lowering of temperature, if delta G is decreasing, then delta H is increasing, and when the temperature is very low, these two becomes equal, and this curve becomes horizontal, and the slope del G by del T at constant pressure, or the delta H by del T at constant pressure becomes equal to 0. And the second, and in some of the reactions also it is found that del H or del G, this one and this one is delta H and this one is delta G. Means with the lowering of temperature, delta H is decreasing while delta G is increasing, and when T becomes near about 0 Kelvin, these two are equal, and this line becomes a straight line. Path becomes a straight line. So these two could be explained by using this relation del G equal to del H minus T del S. Delta G is the free energy change, delta H is enthalpy change, delta S of this entropy change for the processes, and for processes at the constant T and P, constant T and P. So these two curves we can easily explain by the use of this relation. Say for the process, for the process, say delta is equal to negative. If delta is, suppose delta S is positive, means for this process this entropy or the randomness is increasing. So in this case, for these reactions, this delta S is positive, means this one is negative. So delta H is greater than delta G. So with the lowering of temperature, they are approaching towards this equality, and so limit T tends to 0 Kelvin, del H equal to del G. So naturally this curve, this one will be lower, delta G will be decreasing, and delta H is decreasing, and delta G is decreasing with this lowering of temperature. In this case, delta S equal to positive. And if for the process delta S equal to negative, then this one is negative and positive, means delta G is greater than delta H. So in order to get this equality at very low temperature, with the lowering of temperature, this one will decrease and this one will increase, and whenever T tends to 0 Kelvin, these two becomes equal. So in this case, this delta S equal to negative. So by the use of this relation, these two would be explained very nicely. Now I shall discuss the implications of these two formulas. Implications of these two formulas. Implications of these two relations. Already I have told these two innocent pair of relations gives far-reaching implications, and this implication, first implications 1, and first implication is that delta S equal to 0 for processes near 0 Kelvin temperature. This is the first implication. And you know this dg equal to, now I like to formulate how this delta S becomes equal to 0 whenever the T is very low, near to 0 Kelvin. And we have this basic relation, basic thermodynamic equation, dg equal to minus S dt and plus P dt. But in this condensed phase reaction, this pressure V dt. But for this condensed phase processes, the substances are either in solid or in liquid, so effect of pressure is not very prominent, and so at a constant pressure, constant P, whenever the pressure effect is minimum for these reactions occurring in the condensed phases, this dg equal to minus S dt. So, or we can write this del G by del T at a constant pressure equal to minus S. And this is the temperature coefficient, isobaric temperature coefficient of this free energy, and it is equal to minus S. So this is very popular. I have already discussed this one. And for a process, for the initial state, this relation becomes del G1 by del T at constant pressure equal to minus S1. And for the final state, it is del G2 by del T at constant pressure equal to minus S2. S1 and S2, these are the entropy of the initial state and final state for this process, and this G1 and this is the temperature coefficient, isobaric temperature coefficient for the initial state. This one is the isobaric temperature coefficient for this final state. So taking this difference between these two, del G2 minus G1 by del T at a constant pressure, we can write minus S2 minus S1. If this one, we can write this delta G by del T at a constant pressure, then this one will be equal to delta S. But this Nernst heat theorem shows that this one equal to 0 when T tends to 0. So, and this tends to 0, this one also limit T tends to 0, del S also equal to 0. It means that whenever the reaction or the physical transformations occurs near this 0 Kelvin temperature, there will be no entropy change of this reactant and products, or for the initial state and final state. Entropy remains the same. So this third one, I can write here, limit T tends to 0 Kelvin del S equal to 0. This is the consequence. And this consequence gives. Now let us illustrate this consequence. This Nernst statement of this relation has suffered some sort of limitations. we can cite the two limitations. Limitation 1. Suppose let us imagine the formation of these mixed crystals from this pure A and pure B. Say S pure crystal plus S or A pure crystal and B, it is also a pure crystal, and they are forming in an isothermal process this mixed crystal of A and B. So in this process, the entropy change for this mixing process, del S mixing equal to this S of a mixed crystal minus S A pure and minus SB, and this is also pure. This process is occurring near this absolute zero temperature or very near to 0 Kelvin temperature, and delta S mixing will be like this, and this could be expressed as a minus NR into XA and ln XA plus XB and ln XB and XA, XB, these are the mole fractions in the mixture, in the mixed state, and R is the gas constant, N is the total number of moles occurring in this process, and this one is positive. This shows that are not equal to 0. And this actually deviates this Nernst heat theorem. This delta S is not equal to 0, but for this process delta S near to not equal to 0, but the delta S becomes positive, means increasing for this process, though they are this process occurring at near the 0 Kelvin temperature. And second the example, say supercooled liquid forming this solid crystal limit near 0 Kelvin temperature. And for this supercooled liquid is not the stable state, this is the metastable state, and this liquid is having this more entropy than the solid crystals. Here the randomness is much more greater than this one. Naturally, this delta S for this process, delta S of this process becomes negative, means entropy decreasing, randomness decreasing. So delta S is decreasing, so delta S becomes negative and not equal to 0. So I cite here these two limitations where this Nernst heat theorem fails, or delta S is not equal to 0, though the processes are occurring near the 0 Kelvin temperature. So in order to remove these limitations, relations, Simon modified the statement of this Nernst heat theorem, and this is called the Nernst-Simon statement for this Nernst heat theorem. And this statement actually states that whenever these reactants and products are in pure state and each in internal equilibrium, then as the reaction proceeds, there will be no change of delta T, and in turn change in entropy goes to zero as the T also goes to zero. So two criteria, the initial state and the final state of this substance remains in pure state, and each in internal equilibrium. So actually, whenever mixed crystals are not in pure state, and in case of supercooled liquid, this is not in internal equilibrium. This is not the stable state. This is the metastable state for these two. This is why for these two the deviation is occurring. Then another implication. Another implication is the two. We know this is Cp equal to del H by del T at a constant temperature. So for the two states in a process, initial state, final state, for a process occurring near absolute zero temperature, this del Cp change in constant pressure molar heat capacity for this process will be equal to del H by del T at a constant pressure. But since this one equal to 0 when T tends to 0 Kelvin, so limit T tends to 0 Kelvin, this one equal to 0, so del Cp also equal to 0. So this one is the another consequence. Limit T 0 Kelvin tends to 0 Kelvin, del Cp is equal to 0. So these are the very important implications coming from these two Nernst heat theorems. It means that whenever the reaction occurs near the 0 Kelvin temperature, the substances, reactants and products, or the initial state, final state, both are having the same constant pressure molar heat capacity. There will be no change. Now, it will be very surprising whenever we shall calculate or find the expressions of these four thermodynamical properties for a process near this 0 Kelvin temperature. First one, expression of del Cp. We know this del Cp is equal to Cp2 minus Cp1. This is the constant pressure molar heat capacity for the final state, and this one is the initial state of a process. And we have this Cp. Cp can be expressed in terms of the power series of T. Say A plus Bt plus Ct square plus dot. and this is the power series of T, or sometimes also called the virial form of this CP. And A, B, C, these are the characteristic constant of the substance for which this the constant is a molar heat capacity is CP. So for del Cp equal to A2 minus A1 plus B2 minus B1 T plus C2 minus C1 and T square plus dot. These A, B, C, they are the real coefficients. The value of B at least 1,000 times less than A, C is again 1,000 times less than B, and so generally for accuracy, better either 3 terms necessary, 3 terms usually used to get more or less accuracy of the value of the Cp. And this one we can write this alpha plus beta T plus gamma T square plus alpha. If we like to incorporate or comply this relation with this one, with these consequences, then limit T tends to 0, then del Cp equal to 0. So this right and left hand side equal to 0, so alpha plus beta into 0 plus gamma into 0 square plus dot, and this is equal to alpha. So or we can write alpha equal to 0. So in order to comply the expressions of this delta Cp, the relation becomes del Cp becomes beta and plus A equal to 0, beta T and plus gamma T square plus alpha has to be equal to 0, so that this relation is must have to comply this del Cp equal to 0. So this relation is expression is del Cp equal to beta T plus gamma T square, and you know for a process, if we can determine this delta Cp by means of calorimetric study, then beta and gamma could be determined. And these beta and gamma, these terms depends on this process involving these reactants and products. And actually this delta Cp for getting these two values beta and gamma, two equations has to be framed up at two different temperatures. Delta Cp has to be found experimentally, and we get these two equations, and by solving these two equations we can have this beta and gamma. These are obtained and these are known as thermal data for getting this delta Cp value. Now another expressions of and del S. We use this basic equation, this dH equal to TdS plus Vd. dH equal to TdS plus Vdp. So as this condensed phase processes, P is constant. So instead of dH, we can write Cp dt and equal to TdS, or we can write del S divided by del T equal to at constant pressure equal to Cp by T. Cp is the molar concentration, molar heat capacity. And if we consider the process which involves the initial state and final state, this relation becomes del and del S by del P at a constant pressure, and this one equal to this del Cp is by T. If we put here the value of this del Cp here, then this will be equal to beta plus gamma T only plus dot for this other terms or relations. So this d delta S equal to beta plus gamma T plus dot into d. If we integrate these relations, then it will be delta S equal to beta T plus gamma by 2 T square plus dot plus some integration constant delta is 0. Delta is 0. But if we consider the process, whether it is chemical reactions or the physical transformations, this when T tends to when at limit T tends to 0, del S equal to 0. So putting here this 0 equal to T equal to 0, and this, so this term also 0, this term also 0, this one equal to delta S 0. So delta S 0 also equal to 0. So this expressions of this delta S equal to, in terms of this thermal data, this B T and plus gamma y 2 and T square plus dot. This is the expressions of the delta S near the 0 Kelvin temperature. These expressions are getting a bit changed whenever conducted near this 0 Kelvin temperature. And this third one delta H. Delta H. In case of delta H, we know this del Cp equal to del H by del T at a constant pressure. So the del H equal to, writing this delta Cp into dt, and delta Cp equal to this value. So beta T plus gamma T square plus dot into dt. If we do the integration, then 0 to T suppose, and here it is delta G naught. It is the enthalpy change of this process at a 0 Kelvin temperature, and this is the delta H T at this temperature T. So if we do this integration, then del H equal to del H naught plus beta by 2 T square and plus gamma by 3 and T cube plus. And this one is the enthalpy change or the heat of reaction at constant pressure at absolute 0 temperature. Delta H is the enthalpy change for the same process at this temperature T. So we can write this next one, delta H equal to delta H naught plus beta by 2 T square plus gamma by 3 and T cube plus gamma. So delta H for any temperature T would be determined by means of calorimetry, and beta gamma already we know from these expressions of these two substances for undergoing this given process, and so delta H naught would also be determined. And the last one delta G of this process. delta G. We know this delta G equal to delta H minus T delta S. This is the relation occurring at constant temperature pressure. So whenever limit T tends to 0 Kelvin, we can put these relations, these relations here. Instead of delta H, we can write del H naught plus beta by 2 T square plus gamma by 3 into TQ plus dot minus T into, instead of delta S, we can write this beta G plus gamma by 2 and T square plus 1. So the relation delta G is equal to delta H naught, and this one, this minus beta by 2 T square and minus gamma by 6 T square TQ plus 1. So this is the relations between this is the expressions. So this delta G last one is equal to del H naught minus beta by 2 T square minus gamma by 6 TQ plus 1. So actually the expressions of delta Cp, delta S, delta H, delta G, all these expressions are being changed. So whenever we are considering the processes occurring near 0 Kelvin temperature and comply with this Nernst heat theorem. Let us consider a reversible phase transition, say alpha sulfur to beta sulfur, that means anombic sulfur to monoclinic sulfur. At this reversible phase transition occurs at constant temperature, which is called the transition temperature, and at a constant pressure. Say it is alpha sulfur to beta sulfur at a transition temperature and constant pressure. And this is the transition temperature. This is the relation. This is solid. This is solid. This is pure state. This is pure state. Both these two are having this internal equilibrium, having the internal equilibrium. So Simon Nernst-Simon statement is totally applicable for this process. So Nernst heat theorem will be valid, and these relations will also be valid. We can determine this value by the use of these relations. And this is the reversible equilibrium process, reversible phase transitions. So for this reversible phase transition, equal delta G equal to 0. So let us consider this beta equal to 2.30 into 10 to the power minus 5 calorie mole inverse Kelvin inverse square. Kelvin square beta and say delta H is determined for this process equal to 1.57 calorie mole inverse. So these two are already we have determined from this thermal data. So by putting these data in this relation, so 0 equal to 1.57 minus 2.30 into 10 to the power minus 5 divided by 2 into in transition temperature square, and this term is neglected. Is only this value is known to us. And whenever this T epsilon we calculate here, this will be root over 2 into 1.57 and divided by 2.30 into 10 to the power minus 5, and this gives actually the value 369.5 Kelvin. And you know this experimental result, value of T epsilon equal to 368.4. 368.4 Kelvin. So the matching is very nice, and this confirms this validity of these relations whenever the at near 0 Kelvin temperature and some temperature above this above. And change in Gibbs free energy for a process at low. So far I have discussed fully the Nernst heat theorem. So this is a pair of relation I have told, very innocent looking but having a far-reaching consequences. And these consequences or the implications of these two relations are that delta, when T tends to 0 Kelvin, delta S equal to 0 and delta Cp also equal to 0. And from these two again, I have deduced the at low temperature, at constant pressure, delta Cp is expressed as beta T plus gamma T square plus dot dot, and this series naturally terminates after these two terms. As other terms are very low, these series are converging series tending to 0. These are hard terms. So beta and gamma, these are obtained from this thermal data. And so delta S could also be obtained from this thermal data at any temperature T, provided T is at lower temperature. Delta H also equal to delta H naught plus beta gamma related, and delta H naught is the enthalpy change of this process at 0 Kelvin temperature. Delta G, very important term actually in chemical reactions. Delta G equal to delta H naught, and these are the beta gamma terms. And so beta gamma terms are obtained from these relations and by calorimetric study, and by knowing this beta gamma at any temperature, delta S, delta H, delta G, all could be determined. So this most beautiful one is that delta G of a process could be obtained from this thermal data, from this calorimetric determinations. I like to set one example which actually explain all these subject matter actually by these examples. And this example is delta G for a reaction at low T and constant P is given as delta G equal to A plus BT plus CT square. ABC, these are the constants. So that in order to make this consistent with this Nernst theorem, B equal to 0. And the second question, arrive at an expression of delta H and show that del delta G by del T at constant pressure and del delta H by del T at constant pressure have the values equal in magnitude but opposite in sign, and both the values tend towards 0 as T tends to 0. And the third one, plot delta G and delta H against T and show that both are equal at t tends to 0. This is the questions. All the questions could be answered from this. For all these questions could be solved, and it will justify this Nernst heat theorem and other properties also. So this solution of this question is that, of this problem is that del delta G, this is delta G equal to this relations already been given. So del delta G by del T, differentiating this one with respect to temperature at constant pressure is equal to a constant 0, and it is B and plus twice C T. Or according, if this one to be consistent with this Nernst heat theorem, then del delta G by del T at constant pressure must be equal to 0. So if we keep this one equal to 0, then 0 equal to B plus this T equal to 0, so 0, so B equal to 0. So B must have to be 0 in order to make this consistent, make this relation consistent with this Nernst theorem. And now actually B equal to 0, so this equation turns delta G equal to A plus C T square. B is vanished. So this differentiation of delta G with respect to T at constant pressure equal to, this is constant, 2CT. So this is a very important, and delta S we know, delta S equal to minus del delta G by del T at constant pressure. So this relation delta S is equal to minus 2CT. So the second question, the Gibbs-Helmholtz equation shows that delta H equal to delta G plus T delta S. Delta G is having this value A plus CT square, and T here, and delta S equal to minus 2CT. So this simplification of this one will give A minus CT square. So this delta H equal to A minus CT square, and delta G equal to A plus CT square. So again differentiating this delta H with respect to T at constant pressure equal to A is constant minus 2CT. So as the T tends to 0, means T is almost equal to 0. See, this T equal to 0, this one equal to 0. So this one also T tends to 0, means this one equal to 0. So these two are 0, which are the Nernst heat theorems. And again this third one, whenever this delta G and delta H are to be plotted against T, we have this relation, this one and this one, these two. And this relation automatically delta G with respect to T or delta H with respect to T, this will be, plot will be a curve, and this with the rise, with the lowering of temperature, delta G is decreasing and delta H is increasing. Moreover, if we like to find out more concrete idea, then this curvature for this plot, del 2 delta G by del T square constant pressure is positive 2C. This one again double differentiation, it will gives a plus 2C and positive. It means curvature is positive, means this curve will be like this one, curvature is moving upwards, and this curvature, this is equal to first derivative, and second derivative is the curvature, and curvature will give you this minus 2c, and this one is negative. So here the curvature is negative, means it is moving downwards. And whenever the T tends to 0, very low temperature, T tends to 0, these two curves are meeting together, and this delta G and delta H becomes equal, and both are equal to A. Both are equal, and each is having this value of A. If we just casually consider these relations, then A actually will give you the value of delta H naught. Delta H naught in both the cases, and delta H naught is equal to the heat of reaction at 0 Kelvin temperature. So everything have been discussed in this of this subject matter, Nernst heat theorem, and I hope you all will like this video lecture, and if you like, then please subscribe. The next class I shall try to explain the third law of thermodynamics, which is also very important one for this condensed state of these materials. Thank you all.